So everyone has taken stats before this class. So this chapter is really kind of a conceptual review. We're focused on kind of what the statistics are intended to do and how they do that. We're not going to focus a lot on formulas and calculations. This is basically my attempt to condense a semester or more of statistics into one class. Statistics generally have two purposes. One is descriptive. So descriptive statistics summarize the data so that researchers can see what is happening. And they're there to simplify results obtained from research studies. In contrast, inferential statistics help researchers answer questions, determine what conclusions are justified based on the data. So way back in week 6 or 7, I told you to start thinking about what analyses you might use for your project. And as you were planning what variables you measured, you should have had kind of research questions in mind. And so we're going to talk about how to analyze those. So remember when we talk about statistical terminology, there's a difference between statistics, which is a summary value for the sample, versus parameter, which is the value that describes a population. So we're going to start by talking about descriptive statistics. And descriptives are a way to graphically depict scores. So frequency distributions are often a starting point, and so this was a method of simplifying and organizing a set of scores by kind of grouping them into an organized display. Typically, it has kind of two columns of information, the scale of measurement, which is basically all possible responses, and then the frequency of individuals located in each category. So how many people got each score. So this is what a frequency distribution table looks like. So it often shows the distributions of scores. So this one shows the distributions of scores from a 5-point quiz. X is the different scores. F is how many people got each score. So we can see that one person got a 5, 3 people got a 4, and so on. These are the same scores that are shown in a histogram, which is A, and a polygon, which is B. So these show the frequencies as well, but just in a graph. So in this histogram, the x-axis is every possible score, and the bar above each score tells us how many people got that score. The polygon is the same information, but here just a point above each score indicates the same general information. So next we have measures of central tendency. These tend to be very important statistics. Here the goal is to identify the value that is most typical or most representative of the group. And so we might use a line graph or a bar graph to kind of depict these central tendencies, especially if we want to compare group means. So there's a couple of different measures of central tendency we might use. So one is the mean. So this is the mathematical average of scores. We might use the median, which is the score that divides the distribution in half for the 50th percentile, or we might use the mode, which is the most commonly occurring score. And it's important to remember that while we rely relatively heavily on measures of central tendency, the average or measure of central tendency doesn't necessarily tell us all. So these are two distributions that have the exact same mean. But if you look at them, they don't really look the same. So this is depicting the hours of sleep that students got before a 9 a.m. versus 11 a.m. class. And what you'll see is the range for the 11 a.m. class is bigger. The scores are more spread out. We have one student who has 0 hours of sleep and another student who has 13, where all of the students in the 9 a.m. class get between 3 and 9 hours of sleep. So this discussion of the spread of scores is generally called variability. And we have two measures of this, which are standard deviation and variance. So if we look at this, you can look at, for example, the first bullet point, which has more variability. And if you look at A, we've got scores as high as 7 and as low as 1, and there's a pretty big spread. where in option B, all the scores are 3, 4, 5. So there's not as much of a spread. You can also see this next example. What's the variability in this group of scores? Every single score is 4, so there is no variability. So standard deviation is one way to measure this. And standard deviation is the average distance of each score from the mean of a group. So not everyone responds the same way in each condition. So when we look at this standard deviation, we're talking about a deviation, which is how far a score is from the mean. And the standard deviation is the average distance from the mean. Calculating the standard deviation is a bit complicated, but it's important to remember kind of the overarching goal, which is we're looking at the deviation and we want to figure out the average deviation. So to get the average or mean of the deviations, typically we'd add them together and divide by the number of scores. But these deviations indicate equal points above and below the mean. So when you add the deviations together, you always get 0. And so we have to square each deviation to get rid of our negative scores. Then we get the mean, and then we take the square root to get it back to the original metric. So complicated calculations, but essentially we're looking at the average distance of the mean or the square root of the variance. So when we talk about variance, variance measures the variability of the scores by computing the average squared distance from the mean. So we measure the distance from the mean and we square all the differences, compute the average squared distance, and then we take the square root to get it back to the standard deviation. And note that you divide, when you're taking the mean, you divide by n minus 1 instead of by n, and this is to account for sampling errors. We have data that are non-numerical. And so to compute, we don't have numbers to compute a mean or standard deviation. So sometimes we have to use different strategies. So these are normally nominal or ordinal variables. We might use percentages or proportions of people in each category. So, 30% of our sample identified as parents, 70% said they were not parents. Generally, percentages and proportions are essentially different versions of the same thing. Normally, proportions are a decimal point, so they're out of 1, while percentages are out of 100. We might also look at the mode. What is the most frequent response? Next, we might look at correlations. So remember that with correlations, we get 2 scores for each individual. The scores are identified as X and Y. So every person in your sample has a score for X and a score for Y. And this can be presented in a table or a scatter plot. We've talked about these a little bit. And a correlation kind of measures and describes the relationship between these 2 variables. So it tells you about the direction. Positive correlation means that as a score on one variable increase, so does the score on the other variable. And a negative correlation means that they work in opposite directions. As scores on one variable increase, the other variable decreases. We can also get information about the form of relationships. So most commonly we use a Pearson correlation, which measures linear relationships. Non-linear relationships are a little bit harder to measure. We can also look at the strength of the correlation or the strength of the relationship. So this is the numerical value rather than, regardless of the sign. The sign tells us the direction. The number tells us the strength. Correlations are essentially a version of regression. We're not going to do any regressions in this class, but with regression, we're focused on predicting one variable from another. And in particular, we're looking at predicting the slope of the line and the intercept. So where the line crosses the X or the Y axis. So the goal here is to predict Y, or our outcome, when we know a value of X. So you can see that it's kind of similar in strategy to a correlation. Often, when these regressions are really useful is when we want to use multiple predictors to measure our dependent variable. Okay, so if I want to know how gender, socioeconomic status, and college belongingness work together to predict academic success, I would use multiple regression where I can have multiple independent variables working together to predict one outcome. Research questions are almost always about a particular population. And so remember way back when we talked about sampling, we use a sample selected from that population. But of course, our sample is not always going to be exactly like the population. So if we use a different sample, we might get different findings. So inferential statistics are designed to address the issue of how accurately our sample represents a population. And it takes into account sampling error. So this is the fact that the sample does not always provide a perfectly accurate picture of the population. And so it tries to account for the discrepancy or error between the sample and the population. So let's use this example. So let's say we have a population which by some magic we know all about. In the population, we know the average age is 21, we know the average IQ is 112, and we know that the population is 56% female. Now, if we pull a random sample of 5 people, we could get these 2 different samples. In sample 1, we have Eric, David, Laura, Karen, and Brian. We've got an average age of 19.8, an average age of an average IQ of 104, and it's 40% female. We pull another random sample and we get sample 2. And in sample 2, these 5 people have an average age of 20, an average IQ of 114, and is 80% female. So if you look at each of these samples, sample 1 is younger than our population. It's got lower IQ and less female. Sample 2 is close to the age, but still younger, close to IQ, but higher and more female. Neither one of these samples is perfectly representative of our population. So how do we know that the data from our sample is going to represent our population? We figure this out using inferential statistics, and in particular, hypothesis testing. So hypothesis testing is using information from samples to extrapolate to the population. Does our sample data produce convincing evidence to support the research hypothesis? And the goal of the hypothesis test is to ensure the internal validity of a research study and rule out chance as a plausible explanation of the finding. We want to be sure that our independent variable affects our dependent variable and nothing else affects that relationship. So you use different types of hypothesis tests for different purposes, but there are the same basic principles. The first is we start out with a null hypothesis. So this is a statement about a population that says there's no effect, no change, or no relationship. So if we're comparing 2 treatments, our null hypothesis would be that there is no difference. And basically the null hypothesis is that basically any differences that we see are due to chance. So the null hypothesis is always the opposite of our research hypothesis. Another component is the sample statistic. So this is the value of the statistics for the sample. So if we are comparing 2 means, we're really interested in the population means, but we compute the sample means. The value for the population is the parameter. The statistic is the value for your sample. Another important component is the standard error. So this is the average difference between the sample statistic and the population parameter. The test statistic compares the sample statistic to the null hypothesis over the standard error. So this is our t-value for doing a t-test. This is the f statistic. It depends on the specific test, but that's the one we're looking at, that relevant p-value. The alpha level or level of significance is the criterion for interpreting results. How likely are we to accept results by chance? When we decide it's extremely unlikely that we found these results by chance, then we call it significant. So often we use 0.05 as a cutoff, and results, the p-value must be less than our cutoff or our alpha level of 0.05 in order to call a result significant. So hypothesis testing is an inferential process. So what we are doing is using limited information to reach a general conclusion. What this means is there's always a chance of making an error. So there's two ways to think about this, or one way to think about it, but kind of a couple of different dimensions. We always make one of two decisions. Either we conclude that there is a significant difference in the population, or we conclude that there's probably not a significant difference in the population. There are also two possible true outcomes if we somehow knew the truth. Either there actually is a difference in the population, or there actually is not a difference in the population. So this gives us two ways to be right. One is we said there was a difference when there truly was a difference, or we said there was no difference between our groups and there actually is no difference. But it also gives us two ways to be wrong. So the first way is type 1 error. So this is, we say that there is a difference between the two groups and there's actually not a difference. So the researcher finds evidence for a significant result when there actually is no effect. This is called type 1 error, right? So this is the doctor looking at this man and saying, you're pregnant, when he's not actually pregnant. So we mistakenly say there's a difference. That's a type 1 error. We can also be wrong by concluding that there's no difference when there actually is a difference in the population. So this is where the sample data do not show an evidence of a significant effect, but a real effect exists. This is a real bummer, right? You tested for a difference, you concluded there was no difference, but actually there is one. So this is most likely because there's a really small effect. So the difference between the groups is really small, and we assume it's due to chance. So this is type 2 error, or a false negative. We conclude that there's no difference, but really there is. This is a doctor checking out a pregnant woman and saying, you're not pregnant. There's actually something happening there, but we concluded there was nothing. So when we are kind of making these conclusions, there's a couple of factors that might influence whether we find significant results. So therefore, that influence the outcome of a hypothesis test. One is the number of scores in our sample. So a mean difference or a correlation found in a large sample is more likely to be significant than if the same difference were in a small sample. So basically, if we have a large sample, we are more likely to determine or find a significant effect. Variance also plays a role. So if there is high variability or high variance in the scores, we are less likely to find a significant effect than if the same results were found in low variance. So if we think about when we talked about within subjects designs, the benefit of within subjects designs is we have the same participants in both groups, and therefore we dramatically decrease the amount of variability, so we're more likely to find an effect. We've consistently been talking about where to find effect sizes, but effect sizes are really beneficial because they kind of supplement the hypothesis test. And it's more and more increasingly recommended that we include independent measures of effect size like Cohen's d. So effect size basically produces information about the absolute size of the treatment effect. How big of a difference is there? Or how big of an effect is there? And so it's less affected by sample size. So Cohen's d is the most common one. So this is a sample mean difference. So with Cohen's d, you're looking at the sample mean difference divided by the sample standard deviation. You might also look at the percentage of variance. So R squared or eta squared are some measures of effect size for some analyses. And so these look at what percentage of variance in the dependent variable is due to the predictor. Confidence intervals are another strategy for measuring effect size. So here we're estimating the value of the population parameter based on the sample statistic and error. So we show with confidence intervals how large the treatment effect might be. And so this is influenced by the sample size. We say we think the true population parameter is somewhere in this range. So it's really important, kind of the thing that I want to emphasize most for you about statistics in this class is about finding the right statistics for your data. So you need to think about the type of data you have, be thinking about your final project here. If you have ratio or interval scales, then you have numerical scores, and this is compatible with a full range of math manipulations. If you have ordinal scores, then you have rank ordered categories. And if you have nominal scores, you just have named categories. And we can these overlay into three distinct kind of data structures. And we've broken this up in different chapters of your textbook. So descriptive research strategies typically have one group of participants, and we have one variable measured per participant. So we're describing individual variables as they naturally exist. College students at A&M Central Texas get an average of 6 hours of sleep a night. Category 2 is correlational. So in a correlational study, two variables are measured in the same participant. So we've got one group of participants and two or more variables that are measured for each participant. So sleep time, or the amount of sleep that people get, is correlated with grumpiness. So we've got two variables, we measure sleep and grumpiness in the same people and look at if there's a relationship. And then in experimental studies, and kind of looped in with this is true experiments, non-experimental designs where we're comparing men versus women or groups that we haven't created, but we're comparing the groups, and quasi-experimental research designs. So in experimental designs, we're comparing two or more groups of scores where we have the same measurement from different groups of people. So we've got that same dependent variable reported in different contexts or from different people. So with descriptive data, the goal is usually to describe one variable as it exists naturally. We rarely use inferential statistics in descriptive research. We need to know so we only do this if we have a reasonable hypothesis, if we have a specific test value. So this is when we might use that one sample t-test we talked about in the beginning of the semester. Generally with descriptive statistics, we're talking about numerical scores from interval or ratio scales. We can look at descriptive statistics like the mean and standard deviation. We can look at a single sample t-test if we have a specific number we're comparing it to. We might use proportions or percentages to describe the distributions across categories. We haven't really talked about chi-square in this class just because of limited time, but we might use a chi-square test for goodness of fit to compare the sample frequencies to test a hypothesis about the proportions within the population. If you have ordinal scores, you'd probably be looking at the median or the middle score. And with ordinal scores, you can look at proportions or percentages and use chi-square tests to look how likely is it that people are distributed in the way you found, compared to chance or compared to a set standard. And those can kind of tell you about that with that ordinal scale. If you only have nominal data, so you just have named categories, You have even fewer tests that you can use. You normally use the mode as your measure of central tendency, and you can look at what percentage of individuals fall into each category. So you can look at, what percentage of people identify as Republican versus Democrat. And you use a chi-square test for goodness of fit as another analysis you could do. You'd expect by chance that 50% would identify as Republican and 50% would identify as Democrat. How far off were you? Okay, so next with correlational research, category 2, we're looking at what two variables are related, whether they move or change together. So correlations are looking at whether those two variables move together. Regressions are looking at, can you predict variable Y from scores on variable X? And then chi-square test in this context is, can you create or measure groups? So does one variable predict group membership in the other? And then in category 3, looking at these experimental designs where we're comparing groups, the tests you can use depend on your independent variable. So if you have a numerical, the tests you use depend on your dependent variable, your outcome. If you have a numerical outcome, you could use an ANOVA or a t-test. If you have nominal or ordinal scales, you might use a chi-square test to look at predicting categories. If you're using multiple factors, which we haven't discussed yet, but we'll talk about next week, basically multiple independent variables, then you'd use a two-way ANOVA. So in your textbook, the figures 15.12, 1.3, and 1.4 do a really good job of providing the branching type decision tree to help you figure out what analyses are right for your specific research question and the type of data you have. There are some special cases that kind of can help you interpret research results or deal with measurement issues, mostly reliability. So I'm just going to go over them very briefly. Spearman-Brown is a correlational formula to identify split half reliability. So there's two basic concerns in split half reliability. One is that the scores are based only on half of the test scores, and so it tends to estimate the true reliability of the full test. So Spearman-Brown increases the size of the correlation to produce better estimates of the reliability. Kruger-Richardson measures the average correlation from every possible way to split a test in half. So this is limited to tests where each item has only two possible answers. And again, it gives you a correlation that indicates reliability. Another one we use is Cronbach's alpha, which is obtained by considering kind of every possible way to split the test in half. And again, it gives you scores from 0 to 1. And it's often used when you have a measure with, so for example, if you have a measure with 10 items and you want to see how consistent people's responses are on that item, you might use Cronbach's alpha. So all of these are used to kind of assess the reliability of a scale. For behavioral observations, you might need to determine inter-rater reliability. So how consistent are two raters when they observe the same behavior? And Cohen's kappa is basically a percentage of agreements. But correlated for the fact that there will be at least some agreement by chance. So how likely is it that raters agree? So again, this is for observations when you're doing inter-rater reliability. Okay, so the big thing for this week is to work on your analyses. Make sure you've read this chapter if you haven't already. In class, we'll be analyzing your data for the final project. If you have more questions, please don't hesitate to sign up for a meeting with me. The things you will submit are your statistical and analysis reflection, and you can see more about this on the assignment on Canvas, and then you're going to submit your formal results section. There's a separate video that will be posted that will review how to write a results section. Also, you don't have to submit this, but by now you should have gotten my feedback on your method section. And when you complete your analysis in class, you're going to want to run that analyze for that demographic information that you needed. When you wrote your method, you didn't have that information, but by the end of this week, you should have information about the number of participants, gender, ethnicity, anything you measured in terms of demographics, and you can fill in those blanks you had when you wrote your method section. And then next week, we'll cover chapter 11.